Okay, so welcome you all to the week 7 of live interacting session, and the topic is chemical applications of symmetry and group theory. So basically, so we'll be solving previous year assignments or some previous year questions related to this week's content. Okay, so this week basically what we have learned how to find the different normal modes of vibration for a molecule belonging to a particular point group or particular symmetry group. Okay, so let's consider one molecule, let's say ABC. Okay, so this is a molecule consisting of 3 atoms. Okay, so there are 3 atoms, so n equal to 3. Now, so each atom so for each atom there are 3 Cartesian coordinates, right? So for 3 atoms there will be for n atoms there will be 3n Cartesian coordinates. Okay, so number of will be 3n, right? So these Cartesian coordinates, like x, y, z axis of each atom on each atom, x, y, z axis on each atom can act as a basis for irreducible representation. Okay, corresponding to a particular point group. So if you just consider these 3n Cartesian coordinates and perform each symmetry operations on these Cartesian coordinates, you will be generating some reducible representation, and from that reducible representation you can generate different irreducible representation, right? Like how many irreducible representation are there, you can generate from that reducible representation. Okay, now for the 3n Cartesian coordinates, so there will be number of degrees of freedom will be 3n. Like for molecule consisting of n atom, there will be 3n number of degrees of freedom. 3n number of degrees of freedom. Okay, so degrees of freedom, what do we mean by degrees of freedom? Degrees of freedom are basically how many independent coordinates are there. Okay, so there will be translational degrees of freedom. So basically translational degrees of freedom, then there will be rotational, and then vibrational. Okay, so for a nonlinear molecule, there will be 3 translational degrees of freedom. Like overall a nonlinear molecule can move in 3 independent directions, right? X, y, and z. So the overall movement of the molecule is called the translational movement, basically. So a molecule overall can independently move in 3 directions. For a linear molecule or nonlinear molecule, it may be. Then the overall molecule can move in 3 independent directions, x, y, and z. Okay, so for linear or nonlinear molecule, the number of translational degrees of freedom will be 3. And for a nonlinear molecule, there will be 3 rotational degrees of freedom, because there will be 3 independent axes around which the molecule can rotate. Okay, so for nonlinear molecule, there will be another 3 rotational degrees of freedom. Now the rest are basically 3n minus 6, right? This 3n minus 6 degrees of freedom will be vibrational. Okay, so for a nonlinear molecule, number of vibrational degrees of freedom will be 3n minus 6. Okay, now we call this, we can actually generalize these vibrational degrees of freedom. We can represent this as vibrational normal modes. So normal modes basically is normal mode means, so let's consider this molecule ABC, where these 3 atoms can move independently. Like it can go here or it can go there. Like 3 atoms can move independently, but the center of mass of this molecule, the overall center of mass of this molecule will be fixed at one point. Okay, so that particular motion will be called the normal modes. So normal mode means, vibrational normal mode means these 3 independent atoms, or each atom can move independently, but the center of mass of the overall molecule will be fixed at particular point. Okay, those motions can be called normal modes. So these 3n minus 6 vibrational degrees of freedom can be represented as 3n minus 6 vibrational normal modes. So this is important. So for normal mode, the center of mass of the molecule will be fixed at a particular point, but the 3 independent atom, or these 3 atoms can move independently. Okay, so for nonlinear molecule, there will be 3n minus 6 vibrational normal mode, and for linear molecule, so there will be first 3 translational degrees of freedom, because the overall molecule can move independently in 3 directions, x, y, z, right? And there will be 3 rotational degrees of freedom. Sorry, there will be 2 rotational degrees of freedom for linear molecule, right? Why? Because if you consider this type of molecule AB, then, so let's consider this is x-axis and this is y-axis. Okay, now along y-axis or along z-axis you can rotate, this molecule can rotate, but along x-axis if you rotate, so along this molecular axis if you rotate around this axis, then because being this is a linear molecule, so it cannot just, it will generate indistinguishable or identical conformation, right? So if you rotate this, rotate around this axis, around this molecular axis, it will generate identical configuration. So that's why there will be 2 independent rotational degrees of freedom for linear molecule, and the rest will be 3n minus 5, right? So this 3n minus 5 will be vibrational degrees of freedom, or vibrational normal modes. Okay, so this is just the basic concepts. So now in the group theory perspective, so if you consider a molecule and molecule belongs to some particular point group or symmetry group, then there are some possible symmetry operations associated with that particular symmetry group. We have to identify those symmetry operations. Then if you can consider 3 Cartesian coordinates on each atom of that particular molecule, and those Cartesian coordinates, so there will be 3 n Cartesian coordinates, where n being the number of atoms, total number of atoms. So those 3 n Cartesian coordinates can act as basis for some reducible representation. Okay, now you can perform several symmetry operations on those 3 n Cartesian coordinates, and you can generate a reducible representations. Like you can generate character table for the reducible representation. Now from that reducible representation, you can generate, you can get irreducible representation, characters corresponding to the different irreducible representations. Okay, now amongst those irreducible representation, there will be some representations which corresponds to the translational motion, and there will be some irreducible representation which corresponds to the rotational motion. So translational motion means what? So there will be some irreducible representation where linear coordinate like x, y and z will be acting as a basis. Okay, so those irreducible representation will correspond to translational motion. Then the rotational motion means that rx, ry, rz, this type of motion, this type of function can act as a basis for some irreducible representation which will corresponds to rotational motion. And then the rest 3n minus 5 or the rest irreducible representation will corresponds to vibrational normal modes or vibrational motions. So basically the key point is each vibrational normal mode or the combination of vibrational normal mode can act as a basis for some irreducible representation of a molecule belonging to a particular point group or symmetry group. Okay, now let's consider one particular normal mode can act as a basis for some irreducible representation. Now that irreducible representation will be one dimensional, because one normal mode will be one normal mode is acting as a basis. So basis function is one dimensional, that means the dimension of irreducible representation will be also one dimensional. Okay, so basically let's consider one normal mode is acting as a basis. So the dimension of the basis will be 1. So that's why the dimension of irreducible representation will be 1. So it will be like A or B, A prime, A double prime, B prime, B double prime, like this. Okay, now if two normal modes combinedly, the combination of two normal modes are acting as a basis, then the dimension of basis function will be 2. So the dimension of irreducible representation will be also 2. Like it will be E type of irreducible representation. So it will be E type of irreducible representation. Okay, and if 3 normal modes are acting as a basis, then the dimension of irreducible representation will be 3, and it will be T type of irreducible representation, like this. Okay, so basically the key point is this. So each vibrational normal mode or the combination of vibrational normal modes can act as a basis for some irreducible representation of that molecule belonging to a particular symmetry group or point group. Okay, now in the last week we have learned how to find these normal modes and what are the irreducible representation for this normal mode of a particular molecule belonging to a particular point group or symmetry group, right? Now, so this week we'll be looking into how to observe experimentally those vibrational normal modes. Okay, like from spectroscopic perspective, like what will be the group theory perspective on the transition between the normal mode, we'll be learning today, and we'll be solving some assignments. Okay, so before that, let me just check once. Okay, so hi Satish, can you hear me? Hello. Okay, so basically I was just going through some of the contents what we have learned in this week, like how to find the normal modes and how to find the irreducible representation corresponding to a particular normal mode. So now basically the transition, how to observe the transition between different normal modes and how to get this from the group theory perspective. Okay. Okay, so basically, so let's say for water molecule, or for a simple molecule like let's say HF, so it is a linear molecule, right? So the total number of atoms is n equal to 2, so there will be 3 times 2 equal to 6 degrees of freedom. Okay, so translational degrees of freedom, it will be 3, rotational degrees of freedom, it will be 2, and the vibrational degrees of freedom, it will be 3n minus 3 times 2 minus 5, right? Because it is a linear molecule, so there will be 1 vibrational degrees of freedom or vibrational normal mode. Now for H2O, so n equal to 3, so number of vibrational degrees of freedom, it is a non-linear molecule, right? So number of vibrational degrees of freedom, it will be 3n minus 6. So 3 times 3 minus 6 equal to 3. So there will be 3 vibrational normal modes for the H2O molecule. Okay. So 3 vibrational nodes. So basically 3 vibrational normal modes. So let's call this psi 1, psi 2 and psi 3. Okay. Now each vibrational normal mode can be represented by a simple harmonic oscillator, like quantum mechanical simple harmonic oscillator. Okay. So let's call this psi 1, psi 2 and psi 3, 3 vibrational normal mode. Now you want to just experimentally observe these normal modes, like what is the frequency associated with this normal mode. Or normal mode means some particular vibrational motion, right? So like each atom is kind of moving independently so that the center of mass will be fixed. So that particular motion, what is the frequency associated with that particular motion? Okay, if I want to understand this, or if I want to observe this, how do I observe? How would I observe? So experimentally, using different types of spectroscopy like infrared spectroscopy or Raman spectroscopy technique, we can observe this motion, or we can observe these vibrational normal modes. How? Basically, we can observe the frequency associated with that vibrational corresponding frequency associated with that particular vibrational normal mode. So this is basically simple harmonic oscillator. Okay, so what potential corresponding to simple harmonic oscillator, like this, right? Now half k x square, where k is the force constant, x is the coordinate, right? Now there are quantum mechanically there are different discrete levels associated with this simple harmonic oscillator. Now what is the selection rule for the transition? So let's say this is v equal to 0, v equal to 1, v equal to 2, v equal to 3, like this. Okay, so v equal to 0 means a molecule is in ground state. Okay, there is no vibrational quanta, so molecule is in the ground state. Now if I want to observe a particular transition 0 to 1. Okay, so this is, so the, being the simple harmonic oscillator, the selection rule will be delta V equal to plus minus of 1. Okay, so psi 1, so first normal mode psi 1, which is in V equal to 0, and it is going through a transition from psi 1 V equal to 0 to psi 1, let's say V equal to 1. Okay, like this particular transition. Now in IR spectroscopy, in infrared spectroscopy, this type of transition can be, so what actually triggers this particular transition? So there will be a change in dipole moment which can trigger this transition. Okay, so now, so in quantum mechanically, if you write this transition, if you want to write this transition, if you want to represent this transition, you can represent this by direct bracket, like, so from, so your ground state will be psi 1 at V equal to 0. Okay, then in the middle you have to operate, or you have to insert dipole moment operator. Then it will be psi 1 at V equal to 1, like this. Okay, so dipole moment operator is basically driving this transition. Okay, and this particular product is called the transition moment integral, in short TMI. Now if this integration, or if this quantity transition moment integral is non-zero, the value of this quantity, if it is non-zero, then we can observe some transition, or this transition will be spectroscopically allowed, and we can get a peak, okay, corresponding to this transition. Or if this value is 0, then this particular transition from psi 1 V equal to 0 to V equal to 1 via dipole moment transition will be spectroscopically forbidden, and we cannot observe any peak corresponding to this transition. Okay, so basically the basic condition is, if this TMI is non-zero, then transition is spectroscopically allowed. And if this TMI is 0, then it is forbidden, because the intensity of a particular peak, intensity of the observed peak, will depend upon this modulus square of this TMI. Okay, so if TMI is 0, then we cannot observe any peak, and the transition will be spectroscopically forbidden. Now in the group theory perspective, what is this TMI? What will be this TMI? So TMI, so this psi 1 at V equal to 0, or this psi 1, so I just told you, each normal mode or the combination of normal mode can act as a basis for some irreducible representation, right? So this psi 1 can be represented by some irreducible representation, let's say gamma 1. Okay, and this mu, what is the mu? Mu is the dipole moment. So dipole moment means charge times displacement, charge times displacement. So charge, let's say q, times displacement is along x or along y or along z, right? So this dipole moment will be q times along x or along y or along z, right? So this is the, so the dipole moment will be basically linear function of x, y or z, right? So this linear function x y z can also act as a basis for some irreducible representation. Okay, so basically this psi1 at v equal to 0 can be represented by some irreducible representation corresponding to that particular point group. So let's say this is gamma 1. Okay, this mu can also act as, can be represented by some irreducible representation, let's say gamma 2. Okay, now this psi1 also can be represented by irreducible representation, so it will be same as gamma 1. Okay, now this integration in quantum mechanically this integration or this Dirac product, Beckett product, will be converted into, in the group theory, direct product. Okay, direct product between different irreducible representation. Okay. So let's say this psi1 is represented by gamma 1. Gamma 1 is a irreducible representation. Okay, and this mu, which is a function of x, y or z, right, which is a linear function of x, y, z, which is a displacement along x, displacement along y or displacement along z, which can be represented by another irreducible representation, which is, let's say, gamma 2. Okay, so this integration will be converted into, in the group theory perspective, will be converted into gamma 1 direct product, gamma 2 direct product of gamma 1. Okay, now this is the sign for the direct product. Okay, now this direct product can be done from by using the character table. Okay, so basically gamma 1 times gamma 2, gamma 1 is one irreducible representation and gamma 2 is another irreducible representation. So gamma 1 times gamma 2 or gamma 1 direct product gamma 2 can be done by using the character table. That means multiplying the characters of gamma 1 and gamma 2. Okay, and then the output, then you have to multiply another gamma 1 characters of the gamma 1 with the output of these two multiplication. Okay, so this can be done by using the character table of that particular point group. Now if this direct product gives us a totally symmetric representation, let's say if this direct product represents or contains some terms of totally symmetric representation like A1, like this. Okay, totally symmetric representation means the characters of the representation will be all one or will be symmetric with respect to each symmetry operations. Okay, so that is the totally symmetric representation. So this is important. So totally symmetric representation means character of that particular representations will be symmetric with respect to each symmetry operations associated with that particular point group. Okay, now if this direct product of all three irreducible representation contains terms having the totally symmetric representation like A1 prime, like this A1G, etc., then this TMI value will be, this integration value will be non-zero and that particular transition will be spectroscopically allowed. Okay, and if this doesn't give any totally symmetric representation, then this TMI value, integration value, will be 0 and that particular transition will be spectroscopically forbidden. Okay, okay, now Now, how to find that if a particular transition, or whether a particular transition will be x allowed or y allowed or z allowed. That means if you just eradicate the molecule with x polarized electromagnetic field, or y polarized electromagnetic field, and z polarized electromagnetic field, uh, so what would be the fate of that, of a particular transition? Okay, so to find this, it would be like you have to find the TMI corresponding to a transition between, so it will be psi 1 then x psi 1. In the group theory perspective, it will be gamma 1, let's say it is gamma 2, and let's say it is gamma 1 again. Okay, and if this direct product gives us totally symmetric representation, then the corresponding transition or corresponding infrared transition will be x polarized, or along x. If you use x polarized electromagnetic field, then this particular transition will be allowed. Okay, now if you find the, similarly you can find for y direct, along y direction also, y and psi 1, so which will be equivalent to gamma 1 times, let's say, gamma 3 times gamma 1. So now if this direct product gives us totally symmetric representation, then the TMI integral will be non-zero and the transition will be y allowed. If you use y polarized electromagnetic field, then the transition will be allowed, otherwise it will be forbidden along y direction. Okay, now, so what is the condition of getting a totally symmetric representation? Like, what is the condition for this direct product to give us a totally symmetric representation? So basically, this ground state of any normal mode will be totally symmetric representation. Now this is gamma 1 and this is gamma 1. So gamma 1 times gamma 1, that means if you just do the direct product between the same irreducible representation, then it will give us totally symmetric representation like this. Okay, now then the output of that gamma 1 times gamma 1 have to be multiplied with gamma 2. Now the condition will be, so that the irreducible representation of psi 1 and the irreducible representation of x should be same. Then only the direct product will give us a representation having totally symmetric representation. Okay, so the condition will be the irreducible representation of psi 1 and the irreducible representation of x should be same. Okay, or the irreducible representation of the psi 1 and the irreducible representation of y should be same. Then only you can get a totally symmetric representation out of this direct product. Okay, so this is just for infrared. Infrared transition. Okay, similarly for Raman transition, you have to use, so in the infrared spectroscopy, dipole moment is generally used. Okay, dipole moment is kind of driving this transition from v equal to 0 to v equal to 1. Dipole moment is driving this transition. Okay, now for Raman spectroscopy, you have to use the Raman polarizability tensor. Okay, so polarizability tensor basically is a 3x3 matrix, where the matrix element will be basically x square y square, diagonal element will be x square y square z square, and the off diagonal elements will be bilinear product between x, y and z. So x, y, x, z, y, z, like this. Okay, so in infrared transition you are using dipole moment, which is a linear function of x, Y or Z. Okay. Now in Raman transition, you have to use the Raman polarizability tensor. So it is a 3 cos 3 matrix. So it will be a 3 cos 3 matrix. So matrix means it is a rank 2 tensor. Okay. 3 cos 3 matrix where matrix element will be matrix elements are nonlinear product or nonlinear product. Basically it is not a linear function, it is the quadrature function basically. Mane x square y square z square, then there will be bilinear product between x, y and z. So x y, y x, x z, z x, or y z or z y. Okay. Now you have to use this matrix element between two states to get the forbiddenness or allowedness of that particular transition in Raman spectroscopy. Okay. So in Raman spectroscopy, so a particular transition let's say psi 1 at v equal to 0, then via x square psi 1 at v equal to 1. Okay, this is DMI. So basically what I'm saying is that in the infrared transition, here you are using the dipole moment, okay, which is a linear function of x, y or z. But in Raman spectroscopy, here you are using the matrix element of Raman polarizability tensor, which is x square, y square, z square, or x y z, x z or zy, like this. Okay. So in the group theory sense, it will be, let's say, gamma 1 direct product of gamma 2 direct product of gamma 1, and if this direct product contains a totally symmetric representation, then that particular transition will be Raman active. Or if this direct product doesn't give us any representation containing the totally symmetric one, then that particular transition will be Raman forbidden. Okay. Now so using this kind of group theory, like group theory character table, using the character table which that particular molecule belongs to, we can find which particular transition will be infrared active or which particular transition will be Raman active. Okay. So now we'll solve some assignments related to it. Okay, so basically question number 1 is, consider trans PdCl2 N is 3 then whole 2. What will be the symmetry for the Raman active genuine vibrational mode? Okay. Okay, so first, so basically here the question is the trans molecule is given, trans PDCl2 NH3 whole 2. Then we have to find out what will be the symmetry for the Raman active genuine vibrational modes, or what will be the irreducible representation corresponding to the Raman active vibrational modes. To find this, first we have to find out the point symmetry point group for this molecule. Okay, so basically here the structure is PD Cl NH3 NH3. This is the trans one, right? So it also can be represented like this. Okay, so the point group will be D2H. Okay, so the molecule belongs to D2H point group. Now we have to first get the character table corresponding to this D2H point group. Okay, then from this D2H point group we have to find out the what types of irreducible representation will corresponds to vibrational normal modes, like vibrational degrees of freedom, etc. Okay, so basically let me write down the D2H character table first. So number of possible symmetry operations would be E, C2Z, C2Y, C2X, then I, then sigma XY, sigma XZ, then sigma YZ. Okay, now then first representation will be totally symmetric representation. Okay, this will be EG. Why G? Because so D2H point group has inversion symmetry, that means it is symmetric under the inversion operation. So that's why we have to represent, or we have to denote irreducible representation with G or U. G means greater than, or that means it is symmetric under I. Okay, then it will be 1 1 minus 1 minus 1 1 minus 1 minus 1. Minus 1. So here, so it will be B1G. Then it will be 1 minus 1 1 minus 1 1 minus 1 1 minus 1. It will be B2G. You know how to define this irreducible representation using A, B, 1, 2 and G, U notation. Okay, we have discussed this in detail. And then it will be 1 minus 1 minus 1 1 1 minus 1 minus 1 1. It will be B3G. Okay, then it will be 1 1 1 1 minus 1 minus 1 minus 1 minus 1. It will be AU, then 1 1 minus 1 minus 1 minus 1 minus 1 1 1. It will be B1U, B2U, B3U. Okay, so this is the character table. Now we have to write down the basis, corresponding basis. So this is Z, Z, Y, X, and this is RZ, RY, Rx. Then this is x square plus y square plus z square, and then this will be xy, xz, and yz. Okay, now this PD Cl2 NH3 whole 2. Okay, so basically there will be N equal to then 1, 3, means it will be 4 cross 2 plus 2 cross 1 plus 1, 8 plus 2 plus 1. 11 atoms will be there, so there will be total 3n 33 degrees of freedom. Okay, then out of 33 degrees of freedom, there will be vibrational degrees of freedom will be 3n minus 6 vibrational degrees of freedom. So it will be 3 times n means 11 minus 6. (27) will be vibrational degrees of freedom. Okay, so using the Cartesian coordinates, you can just represent the reducible representation corresponding to this 27 vibrational degrees of freedom, and then using the formula we have discussed previously, you can get how many this, but how many of this irreducible representation will give us the reducible representation. Okay, now the question is like, what will be the symmetry for the Raman active genuine vibrational modes? Okay, so basically, so question is Raman active vibrational modes. So we have to find these vibrations. Okay, now the TMI for this Raman spectroscopy was, let's say, for a particular normal mode psi 1, then we have to use the matrix element corresponding from the Raman polarizability tensor, which is the nonlinear product like x square or y square or z square or x y y z or x z, like this. Okay, then you have to use another psi 1. So psi 1 is the wave function corresponding to a normal mode of vibration. So let's say psi 1 is in ground state, so at v equal to 0, then transition is happening from psi 1 at v equal to 1. Okay, So in Raman spectroscopy, you have to use in the middle the matrix element from the Raman polarizability tensor, which is the nonlinear product. Now in the group theory sense, so let's say this psi 1 or this vibrational normal mode is represented by a irreducible representation which is gamma 1. Okay. Now this x square y square xz yz zx, this product, nonlinear product, can act as a basis for some irreducible representation, right? So let's say, so let's assume in group theory perspective, it will be a direct product. Okay. Now let's say gamma 1 is psi 1 is equivalent to, or is represented by reducible representation gamma 1, and the matrix element from Raman polarizability tensor is represented by gamma 2. Okay, so this TMI in the group theory perspective will be direct product between gamma 1, then gamma 2, then gamma 1. Okay, now if this direct product gives us a representation having totally symmetric 1, then this TMI will be non-zero, and that particular transition will be Raman active. Okay, now the condition for this to happen is, so we know that if I just do the direct product between two same irreducible representation, then we can get a totally symmetric representation. Okay, so this gamma 1 and this gamma 1, direct product between these two, will give us a totally symmetric representation, but the output of these two direct product, we have to do the direct product of this output with this gamma 2, right? Now this whole direct product will give us a totally symmetric representation if the irreducible representation for this gamma 2, that means irreducible representation for the matrix element from this polarizability tensor, is similar or same with the irreducible representation representing the normal mode, then this direct product will give us a representation containing a totally symmetric one. Okay, that means this gamma 2 has to be equal with the gamma 1, then only we can get a totally symmetric representation as an output. Then the TMI value will be non-zero, and that particular vibration will be, that particular vibration means this psi 1 normal mode, psi 1 phi equal to 0 to v equal to 1, psi 1 means this gamma 1 representation, that particular vibration will be Raman active. Okay, so the condition for psi 1 or equivalently gamma 1 to be Raman active will be this gamma 1 will be, has to be equal to gamma 2, where this gamma 2 is what? Gamma 2 is the irreducible representation for the matrix, for any matrix element from polarizability tensor. Okay, now it is easy to solve. That means look at this character table here. So there are 1, 2, 3, 4, 5, 6, 7, 8 classes and 8 irreducible representation. We know the number of classes will be equal to number of irreducible representation for a non-abelian group. Okay. Now this x, y and z, this is linear function, right? Okay, x, y, z. Now that means, so Raman polarizability tensor will be bilinear product, non-linear product. That means this x is x, y, x, z and y, z. Okay, these three functions. Okay. So first we have to find out the irreducible representations for vibrational normal modes. Okay. So for the D2H point group, so how to find this irreducible representation of vibrational normal modes we have just discussed. So basically first you have to use the so you have to just, so the here the structure is PdCl NH3 NH3, right? So here on each atom you have to use the 3 Cartesian coordinates. So 3 Cartesian coordinates on each atom you have to use as a basis, and using that basis by performing each symmetry operations on this basis you will get a reducible representation, and from the reducible representation and using the character table you can get what are the irreducible representation for the vibrational normal modes. Okay. So for the D2H point group, so the irreducible representations are like AG, AU, B3U. Okay. So from this, okay, so from these irreducible representations of vibrational normal modes, you have to just match with the irreducible representation corresponding with the quadratic functions, okay, like x square, y square, z square, then x, y, y, z, and xz. Okay, now these particular vibrations will be Raman active. Okay, so Raman active normal modes will be, so here from this character table you can see the x square, y square, z square, or x, y, x, z, y, z. These quadratic function act as a basis for irreducible representation of AG, B1G, B2G, and B3G, right? So that means those irreducible representation, like the vibrational normal modes for those irreducible representation will be Raman active, because I just mentioned the condition for TMI or the direct product will to give us a totally symmetric one will be the gamma 1 equal to gamma 2, where gamma 1 is the irreducible representation of the vibrational wave function for the vibrational normal mode, and the gamma 2 is the irreducible representation for the matrix element from the polarizability tensor. So those two representation will have to be equal, so that our TMI will be non-zero and that particular transition will be Raman active. Okay, now so we just found out that the irreducible representation of vibrational normal modes for the D2H point group will be AG, AU, B1G, B2G, B3G, B1U, B2U, B3U. Now out of these vibrations or out of these representations, quadratic product like x square, y square, z square, xy, xz, yz acts as a basis for the AG, B1G, B2G, and B3G irreducible representation. That means though these four representation will be Raman active. Okay, so Raman active will be AG, B1G, B2G, B3G. Okay, so this is the answer. Okay, why? Because AG represents the x square, y square, or z square. B1G represent xy. B2G represents xz, or B3G represents yz. Okay, that's why. Now the next question is from the same molecule we have to find out the infrared active symmetry for the infrared active vibrations. Okay. Now using the same principle for the infrared active means we have to use dipole moment matrix element. Okay. Now dipole moment matrix element is a linear function of x or y or z. Okay. So our direct product or TMI will be psi 1 then mu psi 1. Okay. So in the group theory sense, this is equivalent to, let's say, direct product of gamma 1 then gamma 2 then gamma 1. Okay. So here gamma 1 is represented psi 1 and gamma 2 represent, let's say, dipole moment matrix element omega mu. Okay. So dipole moment here mu is a linear function of x, y or z, right? Now the condition for this direct product to give us a totally symmetric representation is this. So the condition of this direct product to give us a totally symmetric representation is this gamma 1 has to be equal to gamma 2. Okay. That means the irreducible representation for the vibrational normal mode has to be equal to irreducible representation of dipole moment matrix element or dipole moment function. Okay. So basically from the last question, so the irreducible representations or representations for normal modes for D2H point group are AG, AU, AG, AU, B1G, B2G, B3G, B1U, B2U and B3U, right? Now out of these normal modes we have to find from the character table like the linear function of x, y and z, like x, y and z represents which irreducible representations. Okay, so from the character table you can see that x function acts as a basis for B3U irreducible representation and y is a basis for B2U irreducible representation and z is a basis for B1U irreducible representation. Okay, that means this B3U, B2U and B1U representation, the dipole moment function and the vibrational normal mode, irreducible representation for dipole moment function and the vibrational normal mode will be same for this B1U, B2U and B3U cases. So symmetry for the infrared active, these three vibrational normal modes will be infrared active. Okay, like B1U, B2U and B3U. These three normal modes, that means these three symmetries, okay, will be normal modes can be more than three because like two B1U, like two representations, two irreducible representation can represent two normal modes, right? So these three symmetries or these three irreducible representation will be Raman active. Sorry, Raman infrared active. Why? Because this B1U represents Z and B2U represents Y and B3U represents X. That means, and so these are the linear functions of X, Y and Z, and so the condition will be gamma 1, condition was gamma 1 has to be equal to gamma 2. That means out of these vibrational normal modes or out of these representation, so B1U, B2U and B3U matches with the linear function of Z, Y and X. So that's why these three representations will be infrared active. Okay. So like this you can do for any molecule or any point group. You can find out the infrared active or Raman active vibrations, or which vibrations will be infrared active, which vibration will be Raman active, and in what direction. Actually you can find out from the character table or from the representation of the normal modes, and by matching with the representation of normal modes with the representation of linear function and the quadratic function from the character table. Okay. Now similar question number 3. Question number 3 is consider ammonia molecule and we have to find out the Raman active vibrations. Okay, Raman active modes. So ammonia, and we have to find out Raman active modes. So let's draw the first. We have to find out the point group. Also to find, so first we have to write down the structure. So NH3 is tetrahedral geometry. Tetrahedral geometry means 3 hydrogen atom are there, so it will be C3b point group. Okay. C3b point group, and you can write down the character table corresponding to the C3b point group. Okay. So the possible symmetry operations are E, C3Z and sigma V. Okay. Now the character table will be, so it will be E, 2 C3Z and 3 sigma V. Okay. First one will be totally symmetric representation. It will be A1. Then the second one will be, so 1 1 minus 1. It will be A2, and third one will be plus 2 minus 1 0. It is E representation. Okay. So 3 symmetry operations, that means 3 classes and 3 irreducible representation. Now here it will be Z, this is Rz, this is X Y or Rx Ry. Okay. Now quadratic function, this is x square plus y square this is z square, and this is x square minus y square, xy and xz yz. Okay, this is the character table. Now first, using the Cartesian coordinates on each atom, so that means, so for NH3, so total number of N is 4, right? So 3N will be 4 cross 3 will be 12. Total 12 degrees of freedoms are there and 12 Cartesian coordinates. Okay, now using 12 Cartesian coordinates, by performing each symmetry operations on these 12 Cartesian coordinates, you will get a reducible representations. Okay, and from that reducible representation you can find out how many irreducible representations are there and what are the irreducible representations for translational, rotational and vibrational respectively. Okay, so here vibrational degrees of freedom will be 3n minus 6, that means 6 degrees of freedom. Okay, so here gamma 3n, that means reducible representation will consist of 3a1 plus a2 plus 4e. Okay, okay, so here 4e means e is two dimensional, so that means 4e will represent 4 cross 2 equal to 8 degrees of freedom. 8 plus here 3, 8 plus 3 11, and here 1, this is 12. Total 12 degrees of freedom are there. Now out of this we have to find out what are the translational, rotational and vibrational representation. So translational, you can find out from this character tables. Translation means x, y or z, right? So a1 and e representation will be there. Now there will be 3 translational degrees of freedom. So e representation can give 2 translational degrees of freedom along x and along y, and a1 representation can give 1 translational degrees of freedom along z. So translational will be a1 plus e. Now the rotational, being a non-linear molecule, so there will be 3 rotational degrees of freedom also. The rotational means Rx, Ry and Rz. So Rx, Ry E can represent and Rz A2 can represent. Okay, so E can represent 2 rotational degrees of freedom and A2 can represent 1 rotational degrees of freedom. So rotational will be A2 plus E. The rest would be vibrational degrees of freedom. So vibrational degrees of freedom will be 3a1 plus a2 plus 4e minus translational a1 plus e minus rotational a2 plus e. Okay, so vibrations will be 2a1 plus 2e. Okay, so e can give us 2. E is 2 dimensional, so 2e means it is 4. 4 plus 2 equal to 6. So 6 vibrational degrees of freedom will be represented. Okay, now we have to find out of these a1 and e which representation will be Raman active. Okay, now to get this, so the condition for Raman active vibration will be the irreducible representation for the vibrational normal mode has to be equal to the irreducible representation for the matrix element of Raman polarizability tensor, which is which is a quadratic function of x, y and z, right? So here you can see the x square, y square, this x square plus y square is a quadratic function, z square is a quadratic function which acts as a basis for the a1 representation. Okay, that means this a1 irreducible representation can be Raman active, because this a1 representation for the vibrational normal mode can be equal to the, or will be equal to the a1 representation for the Raman polarizability tensor, which is a quadratic function of x, y and z, right? So a1 will be Raman active, and then this x square minus y square and xy can act as a basis for E, and this x square, xz and yz will act as a basis for E. Okay, and there is E representation for vibrational normal mode also. So that means this A1 and E, both representations can be Raman active. Okay. So Raman active vibrations will be A1 plus E or A1E both. Okay, so this is easy. Like this you can find out the infrared active vibrations also. So vibrations is A1, and vibrational irreducible representation for vibrational normal modes is A1 and E, and then you have to find out what are the linear functions which acts as a basis for A1 and E representation to get the infrared active vibrations. So Z and X, Y both acts as a basis for A1 and E representation. Okay, that means these A1 and E both can act, both will be infrared active also. Okay. Now there is a important theorem which is called the mutual exclusion principle. So which says for a centrosymmetric molecule, centrosymmetric centrosymmetric means the molecule having a center of inversion symmetry. Okay, then that molecule has a I symmetry operation, centrosymmetric means. Okay, so that means they are in the character table of that particular point group, there will be AG or AU representation. Okay, or like G or U representation, like Gerade and unGraded symmetry will be there, because the molecule contains a center of inversion or inversion symmetry. So for a centrosymmetric molecule, no Raman active vibrations will be infrared active. IR active. Okay, that means if a particular vibrational normal mode is Raman active for a centrosymmetric molecule, this is important, like a molecule has to have a center of inversion or inversion symmetry. Then if a particular normal mode is Raman active, then that particular normal mode will be infrared inactive. Okay, so if a normal mode is Raman active, then it will be infrared inactive. Okay, So for a centrosymmetric molecule, this principle is called, from the direct product, you can easily check this. So this principle is called the mutual exclusion principle. Okay. Now, so using the same theory, you can just predict for other point groups or other molecules. Then the question number 3 is, say all wave functions for normal vibrations in their ground state are the dash for the at the basis for the of the point group to which it belongs to. Okay, so all wave functions for normal vibrations in their ground state. So we have discussed all the or the ground state wave function for all normal modes can act as a basis for a totally symmetric representation. Okay, that means ground state wave function will be symmetric with respect to every symmetry operations corresponding to that particular point group. Okay, so the answer will be, it can act as a basis for totally symmetric representation. Okay, so like this there are, so all other questions are basically kind of repetitive. So using the basically same principle, you can do all the assignments. Basically you have to find out the character first. You have to find out, so for a particular molecule, you have to find out the how many vibrational normal modes are there, and then what are the irreducible representation corresponding to those normal modes, and then which vibrational mode will be Raman active and infrared active. To answer this type of questions, first we have to define the point group of that molecule, then you have to write down the character table, and using the character table you can just define the which particular linear functions are the basis for which representation. Okay, then by just matching the irreducible representation for vibrational normal modes with the linear functions x, y, z, or the nonlinear function x square, y square, z square, or x, z, y, z, you can get the vibrations which will be Raman active or infrared active. Okay, so to be a particular vibrational mode Raman active, then that the irreducible representations for that particular vibrational mode has to be equal to the quadratic function, irreducible representation of the quadratic function, like the matrix element for the polarizability tensor. And to be infrared active, the irreducible representation for the vibrational normal mode has to be equal to the linear irreducible representation for the linear function of x, y, and z. Okay, like this. Okay, so see you in the next week.